Welcome back to The Explainer. Today, we're unpacking a massive cosmic mystery hiding right in our own galactic backyard, the Araya constellation. We're looking at Caldwell 86, an ancient structure where the standard rules of stellar evolution are pushed to their absolute extreme limits. It's left behind an invisible puzzle that astrophysicists have literally spent decades trying to solve.
To really grasp the scale of what we're dealing with, let's start with a massive question. Imagine taking 400,000 stars and cramming them into a space so tight they're practically bumping shoulders. We're talking about a stellar density millions of times greater than our own local neighborhood around the sun. When stars are forced into that kind of extreme proximity, what happens to all that mass? Where does all that immense gravitational energy actually go? Well, we're going to unravel the secrets of this truly unique astronomical anomaly step by step.
Section 1. Meet Caldwell 86, a globular cluster in the Era constellation.
Located just 8,000 light-years from Earth in the Era constellation, Caldwell 86, also known as NGC 6397, was discovered all the way back in 1752. Globular clusters like this one are some of the oldest structures in the universe. They're essentially these giant spherical metropolis of stars orbiting the outer halo of our Milky Way. And in galactic terms, a distance of 8,000 light-years is incredibly close. That proximity is an absolute gift to modern astronomers because it gives us an unprecedented front-row seat to resolve its individual stars and study its internal mechanics with just incredible precision.
And packed into that ancient spherical structure are roughly 400,000 individual stars, but they aren't spread out evenly. The sheer concentration of mass localized right in the center creates this intense gravitational pressure cooker. And it's exactly this extreme density that sets the stage for the highly volatile stellar interactions we're about to explore.
Section 2. Anatomy of core collapse. Basically, a cosmic mosh pit.
Over its roughly 13 billion-year evolution, Caldwell 86 has turned into an environment that behaves a lot less like a peaceful starry night and a lot more like a cosmic mosh pit. This happens because of a fascinating astrophysical process called core collapse. As stars move through this crowded cluster, they experience dynamical friction. Because of a trend toward what physicists call the equipartition of energy, the heavier stars lose kinetic energy and sink down toward the center, while the lighter stars get kicked out to the edges. Over billions of years, this creates a runaway effect. The heavier stars pack so tightly together, they form an incredibly dense core, fundamentally altering the cluster's internal dynamics and completely blinding our standard optical telescopes with their concentrated glare.
Section 3. Chandra's X-ray discoveries. Peering through the glare.
Since the center of Caldwell 86 is just a blinding glare of tightly packed stars, astronomers had to change up their methodology and turn to the Chandra X-ray Observatory. When you view this cluster in X-rays, the blinding visible light of normal main sequence stars is totally stripped away. What you're left with are these bright, energetic signatures of extreme objects hiding right in the core. To emit X-rays, material has to be heated to millions of degrees, which means the objects lurking in the center of this cluster are operating under unimaginably extreme physics. And Chandra's data revealed a core teeming with exotic compact binaries. You see, the cramped quarters of a core-collapsed cluster literally force stars to interact, stripping material from one another and pairing up. The data picked up cataclysmic variables, which are systems where a dense white dwarf cannibalizes gas from a companion star. It spotted millisecond pulsars, these rapidly spinning neutron stars acting like high-energy beacons sweeping through the dark. Researchers even identified quiescent low-mass X-ray binaries, emitting thermal heat from their deep stellar crusts. It is a highly active, turbulent neighborhood where close stellar encounters are just a daily reality. But despite finding all these brilliant X-ray sources, the cluster's most massive feature was actually completely invisible. By closely tracking the kinematics, meaning the precise velocities and movements of stars swirling in the cluster, researchers realized an unseen dark core was pulling on everything else. We are talking about 1,000 solar masses of completely invisible material localized right at the innermost center of Caldwell 86. Now, the immediate assumption for most of us would be an intermediate mass black hole. But if it wasn't a giant black hole, what on earth was it? Section 4. The Missing Mass Mystery. Investigating the Shadows. To solve this paradox, astrophysicists compared Caldwell 86 to a normal, non-core collapsed cluster, like NGC 3201. A non-collapsed cluster has a flatter, wider core because it still retains a large population of stellar mass black holes.
When these black holes interact with passing stars, they transfer kinetic energy outward, a process known as binary heating. This effectively props the core up, keeping it kind of fluffy. But for Caldwell 86 to reach its highly condensed, steep core collapsed state, dynamical models tell us it must have ejected almost all of its black holes millions of years ago through violent multi-body interactions. Once those black holes got kicked out of the cluster, the core lost its heating source, and the center simply caved in.
Section 5. A dense stellar graveyard, the true nature of the dark core. So, with black holes firmly ruled out by the physics of core collapse, the data pointed to a stunning reality hidden inside the innermost 0.07 parsecs. Enclosed mass profiles, mapped out through super-precise observations of stellar orbits, confirmed that the invisible gravitational anchor at the center isn't a single point of mass, like a supermassive black hole. Instead, it's an extended, diffuse subcluster made almost entirely of dead stars, specifically an incredibly tight swarm of white dwarfs. And this isn't just a loose collection of dead stars. It is a remarkably heavy, centralized graveyard. Roughly 2/3 of this dark mass consists of carbon-oxygen white dwarfs. Those are the dense, cooling cores left behind by dying sun-like stars. The rest is made up of even heavier oxygen-neon-magnesium remnants. Throw in a few scattered, highly magnetized neutron stars, making up about 30 solar masses, and you've got a dark, dead core that heavily outweighs all the living, luminous stars actively burning around it. Section 6. Cosmic collisions and ripples. The fate of the graveyard. Okay, so what actually happens when you pack all these dense, dead stars into such a tiny cosmic footprint? Well, they definitely don't rest in peace. Thanks to constant, chaotic gravitational encounters in this mosh pit, white dwarfs routinely capture each other to form tight binaries. As these binary pairs interact with a third passing star, they undergo a process called hardening. The third star gets ejected at a high velocity, stealing orbital energy from the binary pair, which forces the binary to shrink. Over time, as they spiral closer and closer together, gravitational wave emission takes over, pretty much guaranteeing that these dead stars will inevitably and violently collide. These extreme mergers have massive implications for modern astrophysics. As these white dwarfs spiral inward and literally rip each other apart, they generate millihertz gravitational waves, actual ripples in the fabric of spacetime that future space-based interferometers like the LISA mission are going to be able to hear. Depending on their combined mass when they crash, these mergers can trigger cataclysmic type I supernovae, they can fuse into single rejuvenated massive white dwarfs, or if they push past the Chandra sacral limit, they can even collapse into young neutron stars capable of firing off powerful fast radio bursts. Honestly, it's profound to think about. Just 8,000 light-years away in the Ara constellation, an invisible stellar graveyard is actively burning through its own dead. By constantly forcing these tightly packed white dwarfs to interact and merge, the cluster generates just enough dynamical energy to heat its core and hold off a complete gravitational collapse into a central black hole. It is this incredibly delicate, violent balancing act playing out on a massive cosmic scale. And that leaves us with one fascinating final thought for this explainer. If a whole, hyperdense graveyard of hundreds of dead stars can hide in plain sight, masquerading perfectly as a black hole until we looked closely enough at its internal dynamics, what else is out there? What other invisible cosmic mysteries are just waiting in the dark to be uncovered by our next generation of telescopes? Thank you so much for joining me today. Keep looking up and stay curious.